All right, hi everyone. In this video, I'm going to be going through pH formulas with more of a focus on just getting through some sample problems, not so much the origin of these pH scales. Excuse me. So these are the 6 pH related formulas, and basically these can all kind of be derived from one another. So if you're a little more comfortable with logs and like exponents, you could probably see, only memorize a couple of these, and then you can kind of work out the rest. But these are the 6. So if you're watching this in 2021, we are not requiring you to memorize these. That may change in future years of chemistry students. But again, I would just write these down. But the main idea is knowing which formula to use when. It's like there's a right tool for every job. So let's go through each of these 6 formulas and talk about when you want to actually use them. So the first 2 formulas are the ones we've already talked about a lot. It's like the origin of pH and POH. When you know the concentration of hydronium, now there are certain terms you should be very familiar with. This is hydronium, this is hydroxide, and the brackets mean concentration of or molarity of. So when you know the concentration of hydronium or the concentration of hydroxide and are looking for pH or POH, you're going to use these. So notice it says pH equals and POH equals, and you just plug it in as negative log of that hydronium or that hydroxide. Remember, the unit for concentration of is molarity, and pH and POH have no unit, they're just numbers. So for example, what's the pH of a solution whose hydroxide concentration? Oh, you know what? I meant to say this differently. We can solve this, but I don't want to use this as my first example. Let's call this POH. What is the POH of a solution whose hydroxide concentration is 0.0318 molar? So, simple plug and chug. We're looking for POH, negative log of 0.0318. They might say, why do I have brackets here, but parentheses here? Well, this number is the bracketed concentration of. So, I mean, you could put brackets if you really want, but like the idea is that number is the molarity, which is represented by the brackets. All right, so negative log of 0.0318. So in my calculator, I plug that in. And we want to be consistent with sig figs here. 3 sig figs, 1.50. And remember, pH and POH do not have units, they are just numbers. When you know the pH or POH and want to know POH or pH, so essentially when you know one but want to know the other, you're simply going to use this one, the simplest of the formulas. Now this 14 is like a perfect 14 or like 14.0000 dot, 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 and so on. So, don't cut it off to whole numbers. So for example, what's the pH of an acid if POH equals 10.7? So if we want to solve for pH, pH is going to equal, just subtract POH out of there. 14 minus POH, which gives us 14 minus 10.7, which is going to be what, 3.3? Just confirm. It'd be embarrassing to get that wrong. Yeah, 3.3. That's my pH. Now, you might say, well, hold on, what about sig figs here? Well, technically, we are subtracting. We are not multiplying or dividing, so we don't care about sig figs. What do we care about? Decimal places. Now, this 14, as I said before, is a perfect infinite 14, so call it 14.0000 forever. So we're not going to limit our decimal places because of that. So we're going to use the tenths place here and a tenths place here. And you might say, well, hold on, didn't you just cut a sig fig out and go from 3 to 2? Technically, yes, but this is still the right way to represent it. 3.3 is the pH. What if you know one of these concentrations and want to know the other one? Well, now you're going to use formula 4, where the concentration of hydronium times the concentration of hydroxide is 1 times 10 to the negative 14. And this is, again, a perfect 1. So call it 1.000 times 10 to the negative 14. Now, technically, there is a unit here. Since the unit of this is molarity and the unit of this is molarity, technically it's molarity squared, which is a little strange, but it does work out so that one of the molarities cancels out. Now, I will say for this one, since you're usually going to be dividing by a number in scientific notation, you need to either use parentheses or the E function if you're dividing by scientific notation. Okay, if you don't, calculator is going to say the wrong answer. Okay, so if hydronium concentration is 2.18 times 10 to the negative 9 molar, what's the hydroxide concentration? So we know one, we want to know the other. So manipulating the formula above, OH minus concentration, we need to divide this out of here. So it's going to be 1 times 10 to the negative 14, technically molarity squared, divided by concentration of H1, concentration of hydronium, which is 2.18 times 10 to the negative 9. Oh, to the negative 9. Okay. Now again, with your calculator, you can say 2.18 e negative 9 if you know how to use the E function, and that's the single capital letter E, not lowercase e, or put that in parentheses. It's also worth noting, if I'm taking the negative 14 and dividing it by negative 9, that's the same thing as subtracting. So it's worth it to take a few seconds and check. So negative 14, negative 14 minus negative 9, what's that going to equal? Well, minus negative 9 is the same thing as saying plus 9. And what's negative 14 plus 9? Negative 5. So in the back of my mind, I'm thinking negative 5, and this will always be within a range of 1. So it might be a negative 4, or a negative 5, or a negative 6. It's going to be one of those three. And when I say it will be, I mean the exponent. So it's worth it to take like 15 seconds, check your exponent, and say, what should it end up being? It should be one of these three. And if it ends up being totally wrong, you know you maybe forgot parentheses or something like that. All right, so 1, I'll use the E. 1e negative 14 divided by 2.18 e negative 9 gets me, checking my sig figs here, 3 sig figs. So 4.59 times 10 to the negative 6th, which makes sense. My unit for concentration is molarity. If you know the pH or pOH and want to know hydronium concentration or hydroxide, so this is like the opposite of formulas 1 and 2. So before it was if you know the concentration and want to know pH. Now, if you know the pH and want to know concentration. So remember, like I said, it's the right tool for every job, so use the right formula. So this one's actually a little trickier, but we can go through it. What is the pOH of a 0.0395 molar strontium hydroxide solution? Assume 100% dissociation. So when strontium hydroxide, which in this case is going to be a strong Arrhenius base, dissolves in water, it's going to split up into ions. And we're going to get 3 ions from this. We're going to get a strontium ion. We're going to get a hydroxide ion. We're going to get a second hydroxide ion because the 2 hydroxides are going to split. So with this in mind, if we assume 100% dissociation, then for every 1 strontium hydroxide, we're going to get 2 hydroxides. Or in other words, if the concentration of strontium hydroxide is 0.0395 molar, the concentration of hydroxide ions is going to be twice that, 0.0395 times 2, because for every one of these, you're going to get 2 hydroxides. So I'm going to double this and say 0.079 molar. Technically with 3 sig figs, I'll stick a 0 there. And now that I have my hydroxide concentration, simply plug and chug. You know what I just realized? This example I made up doesn't actually fit this one. Whoops. Well, I'm not going to go back and redo this whole video. But if I'm looking for pOH, I'm not going to use this formula. I'm going to use negative log of the hydroxide concentration. So negative log of 0.0790 gives me a pOH of 1.10. Okay. Now, what would a real example like this look like? Well, it'd be pretty simple and straightforward. It would say, if the pH of an acid is 2.17, what's the concentration of hydronium? And you would just say 10 to the negative 2.17, which in that case would be 0.00676 mole. All right, so here's a sample, like a grid, where we can kind of get some rapid fire answers here. Now remember, there are 6 formulas, and there's a right formula for every job here. So for this one, if I give you the concentration of hydronium, and I'm looking for all 3 of these, you can really go in any order you want. So if we're looking to find OH minus, let me just go right here. If I know one concentration and one know the other, which of those formulas should we use? You should look at your list where you have 1 through 6. And remember, if you know one and want the other, you're going to use formula number 4, which is the one with the 1 times 10 to the negative 14. So I'm going to say 1 times 10 to the negative 14 divided by 0.0217, which gets me 3 sig figs, 4.61 and -13 mole. Okay, now if we're looking for pH, so formula 1, pH equals negative log of the hydronium concentration, which is right here. Negative log of 0.0217 gives me 1.66. And once I know pH, pOH is very easy. I'm just going to go 14 minus that. And with 2 decimal places, I get 12.34. And just so you know, if you solve these in a different order, your answers might be slightly different. And that's because due to the logarithmic nature of the pH scale, the fact that every difference of 1 is really 10 times different, a lot of times a very small difference will become amplified. So, let's say you started with this and you found the pH first, which you would do that using negative log of 0.0217. And then from the pH, you found pOH. And then from the pOH, you found concentration of hydroxide. Your answer might be slightly different, kind of more different than we're used to. You might end up with something like 4.37 times 10 to the negative 13, or maybe 4.71. And that's totally fine, because those little minute rounding differences end up getting amplified tenfold. All right, let's do the next one. So for this, we have 12.75 as a pH. Let's see what we can solve for. If we have the pH, let's go ahead and solve the hydronium concentration. So we're going to say 10 to the negative pH. So 10 to the negative 12.75 gives me a hydronium concentration of 1.78 times 10 to the negative 13. And my unit for that is molar. And let's see where we can go from here. Let's go ahead and find pOH. So 14 minus 12.75 gives me 1.25. Now that we have pOH, let's find OH minus. 10 to the negative 1.25 gives me 0.0562 mole. Now you might say, like, well, do we need to use scientific notation here? And the answer is no. Just use a scientific notation if the number is kind of ridiculously large or small. I'm not going to write this in normal form because that'd be 0.000000000000178. For that one, I'm going to use scientific notation. But if you want to say 5.62 times 10 to the negative second, you're welcome to do that. But I'll just write it in normal form. Okay, for the last one, I have one concentration. I want to know the other plus the pH and pOH. So if we look at what I did number 1, I just immediately found the other concentration. For this one, let's go a different way. If we know OH minus, let's find pOH. So pOH is going to be negative log of the hydroxide concentration. So negative log of 5.17 E negative 8 gives me a pOH of 7.02. 29. And once we have pOH, let's find pH. So it's simply 14 minus that, which is 6.71. And now that we have pH, let's find concentration. So we say 10 to the negative 6.71, which gives us 1.95, 10 to the negative 7 mole. Okay. And let's just go through a couple Utexis questions. These are questions off the Utexis 20. So your questions are probably similar to these, but not exactly the same. So just be careful with these. All right, what's the pH of a 2.4 times 10 to the negative 5th molar HNO3 solution? That would be nitric acid solution. Now, something that's not stated here, but we should know, is that HNO3, aqueous acid, okay? And that should be in your notes somewhere. And what that means is that 100% of this will dissociate. So if you're given the molarity of an acid, and we know it's strong, then for every HNO3, we're going to get one H plus and one NO3 minus. And of course, that H plus will immediately turn into H3O plus. So notice that for every one of these, we're going to get one of these. Or in other words, the concentration of HNO3 is going to equal the concentration of H3O plus. It's like a 1-to-1 ratio. Any monoprotic strong acid will give you a 1-to-1 ratio. So for this one, my concentration of H3O plus is going to equal my concentration of the acid, which is 2.4 10 to the negative 5th. And now that I have this, I'm just going to solve for pH. So let's use formula number 1. pH is negative log of 2.4 times 10 to the negative 5th. Negative log 2.4 e negative 5 gives me a pH of 4.62. So we can see matches right there. All right, next question. So if 17.6 grams of HCl are used to produce a 14.5 liter solution, what's the pH? Okay, so what can we do here? Well, it gives us grams, so you can probably figure we're going to be turning that into moles. And now once we have moles and liters, we can find molarity. And that's going to give us our molarity of HCl. Now, similar to the last question, HCl is a monoprotic strong acid. So the concentration of HCl is going to equal the concentration of hydronium ions that come from that. It's like a 1-to-1 ratio because there's one H plus, which turns into hydronium. So the molarity of my HCl equals my molarity of H3O plus. And once I find this, pH is simply negative log of that. Brackets, H3O plus. Okay. So let's turn our grams into moles. 17.6 grams of HCl. 1 mole over, let's see, 35.456 is Cl plus 1.1. 36.7 grams. This gives us 0.483 moles of HCl. And if we take our moles and divide it by our liters, that's going to give molarity. 0.483 divided by 14.5 means that my molarity of HCl is 0.0333 molar. And that means that my concentration of H3O plus is also 0.0333 molar. And now I could find pH by plugging that in. Negative log of 0.0333 gives me 1.48. Now remember, with Utexis, go ahead and enter the full number. So technically my calculator says 1.47755. All right, I think this is the last one here. So assuming that the phosphoric acid is completely dissociated. Now phosphoric acid should be in your notes, H3PO4. molarity be of hydrogen ions in a 1 molar H3PO4 solution? Now, this is actually not a pH calculation problem. It's more like a theory question. So if this fully dissociates, what are we going to get? We're going to get 1H plus, 2H pluses, 3H pluses, and a phosphate, because this is a triprotic acid. And of course, each of these H pluses are going to turn into hydronium. In reality, this is what we're really going to get. A triprotic acid, if it fully dissociates, will give you 3 hydroniums plus whatever your anion is, the negative ion. So the concentration of this compared to the concentration of these hydroniums, it's like a 3-fold increase. See that? For every 1 H3PO4, you're going to get 3 H3O pluses. So if my concentration of H3O plus, my concentration of H3PO4 is 1 molar, then my concentration of H3O plus is going to be, think about it, 3 molar. So no need to use any kind of pH calculations here. Now, of course, they could ask for the pH, and if we know my concentration here, we would just say that pH equals negative log of 3. Negative log of 3 gives me negative, well, 1 sig fig 0.5. pH is negative 0.5. Now, you might say, I thought pH couldn't go below 1, couldn't go below 0. It's not true. It can go below 1, it can go below 0. In fact, if the pH, if the concentration of hydronium, H3O plus, if it's exactly 1 molar, it's going to have a pH of 0. So if it's anything stronger than 1 molar, like in this case, you're going to have a pH of less than 0. So there's actually no limit to pH. Okay. So good luck with these. You can now work on the rest of these Texas questions.